Hi students, in this chapter we will learn about different properties of matter. We will learn, for example, about the phenomenon of surface tension, which is responsible for the formation of soap bubbles. We will learn how objects expand and contract. That is, we will learn about elasticity, what happens to a body when we apply some forces on it. And we will even learn about viscosity, which represents how thick, or how light a liquid is. So we will learn about viscosity, surface tension and elasticity, the different properties of matter. So let's start off with viscosity. So what is viscosity? When you look at a fluid flowing, a liquid flowing for example, then the friction force between the different parts of the liquid is termed viscosity. What does that mean? Take a look at water flowing, on this wooden surface. If you really go close and magnify what is happening, then you will see different layers slipping over each other as water flows or as any liquid flows. The layer that is in contact with the floor is at rest. After all, the floor is at rest, so the layer in contact with the floor is also at rest. But the other layers are slowly drifting apart, and that is how liquid flows. In fact, what is the flowing of a liquid? Flowing of a liquid means that one part of the liquid slips relative to another part of the liquid, isn't it? When a solid moves, the entire solid moves at once. But when a liquid moves, a part of the liquid slips over other parts of the liquid. Viscosity represents the friction between the layers of the liquid as they slip over each other. Understood? It is the friction between these layers that opposes the relative motion between the layers that viscosity represents. In fact, viscous force is the force that opposes the relative motion between the layers. Understood? That is what viscosity represents. So the more the viscous force, the lesser the liquid will flow, because the more the opposition to the motion between the layers will be. Isn't it? And the lesser the viscous force, the more easily the layers will flow, and the liquid will flow very, very easily. Newton found out a relationship between the magnitude of the viscous force and some other parameters related to the liquid. He said that the viscous force F is proportional to dV by dz. Now what is dV by dz? dV by dz is the rate of change of velocity of the layers with respect to height from the bottom. So for example, if Z represents the height of any random layer and V represents the velocity of any random layer, then the rate of change of velocity with height is termed dV by dz, isn't it? Delta V by delta Z, how the velocity of the layers changes as the height keeps on increasing. So the bottom layer has zero velocity, then the velocity increases, then it further increases, then it further increases. The rate of increase of velocity with height is what the viscous force is proportional to. Understood? So if the rate of increase of velocity with height of the layers is very high, then the viscous force will also be very high. If this rate is gradual, then the viscous force will be less. In fact, this is what Newton found out. He also found out that the viscous force is proportional to the area of the layers. This means that, if you have water slipping over a small narrow surface, then the viscous force will be less compared to, if you have a river flowing, that is huge layers of water slipping over one another. So the viscous force is also proportional to the area of each layer. Understood? And this was the final expression that Newton devised for the viscous force. This viscous force is minus eta A dV by dz, where eta is constant for any particular liquid. The minus sign has been put in here because the viscous force is a resistive force, isn't it? So it always acts opposite to the direction of the velocity of the layers, V. Eta is also called the coefficient of viscosity. Understood? As I said earlier, it is constant for every substance. Viscous force is of course measured in Newton, and it represents the resistance between the different layers of a liquid. The coefficient of viscosity has the unit Newton second per meter square or Pascal second. It is also measured in a special unit called poise, such that 10 poise or 1 decapoise are equal to 1 Pascal second. Understood? So 10 poise are equal to 1 Newton second per meter square. The higher the coefficient of viscosity of a body, the more the resistance between its layers and the more difficult it is for the body to flow. So honey has higher viscosity than water, the coefficient of viscosity. That is why honey doesn't flow as easily as water, because the resistance to the flow of layers is more in honey. Understood? These are the dimensions of the coefficient of viscosity. Another interesting thing we must learn, and you must keep in mind, is that this kind of flow in which there are perfect layers which flip over each other is often called streamlined flow or laminar flow. Understood? In reality, we don't have such perfect layers. There are some breaks between layers. Sometimes the layers are not perfect cuboids like this. But if we assume that the layers are perfect and they perfectly slip over each other, then the flow is called streamlined or laminar flow. Let's solve a problem. A boat with flow area 5 meter square is moving with a velocity of 2 meter per second over a water body of height 1 meter. The floor of the pond over which the boat moves is at rest. The velocity of the water varies with height as v equal to 0.01 y square, where y equal to 0 represents the bed of the pond. So there you go. This is what is happening. A boat is floating in water. The height of the water from the bed is 1 meters. The area of the bottom of the boat is 5 meters square. What is the viscous force on the floor of the boat? The viscosity of water is 0.01 poise. Again, what do we do? This is what is given in the question. Here you can see the boat is floating over the water. The viscous force on the bottom of the boat is clearly minus eta A dv by dy. That's the formula for the viscous force. The viscosity of water is given. The area of the boat surface is given, isn't it? dv by dy is what we need to find out. Now it is given that the velocity of the pond water varies with height above the bed of the pond as v equal to 0.01 y square, isn't it? Y is the upward height of any point from the bottom of the pond. So since v is 0.01 y square, dv by di, the rate of change of velocity of the layers of the pond with respect to height above the bed is 2 into 0.01 into y, isn't it? Which comes out to be 0.02 y meter per second. Now at the surface of the pond, the part of the liquid that actually applies the viscous force on the bottom of the boat, dv by dy is 0.02 into 1 meter, isn't it? So the viscous force at the bottom of the boat is minus eta A into 0.02 into 1 meter. This comes out to be 10 raised to minus 4 Newton. So we have just put the value of dv by dy for y equal to 1 meter. There you go. That's our answer. The boat experiences a viscous force of 10 raised to minus 4 Newton. For more explanations and for more problems like this, do log on to TopCoaching.com's physics section. Let's now move on and learn about another interesting concept, the concept of Stokes' law. You see, until now, we have calculated the viscous force on a surface, isn't it? After all, the viscous force we have calculated is the viscous force between two layers, or it is the viscous force between a liquid and a solid, isn't it? But we have calculated the viscous force acting on surfaces. What if you have a spherical ball that is floating through water or through mercury or through oil or through any fluid? How do we find out the viscous force on that spherical body as it moves through a fluid? Stokes' law is a law that tells us the value of viscous force that acts on a spherical body as it moves through a fluid. It was given by Graham Stokes. According to Stokes, the viscous force acting on a spherical body moving through a fluid is 6 pi eta rv. Here eta is the coefficient of viscosity, r is the radius of the body that is moving through the fluid, and v is the velocity with which the body is moving through the fluid. Here we go. Take a look at this ball moving through water, something like this. When a ball is moving through water like this, a force 6 pi eta rv, the viscous force, acts on this ball. This force always acts in the direction opposite to the velocity of the ball. Understood? Since the ball is moving downwards, the force acts upwards. Understood? Now a very interesting phenomenon occurs because of Stokes' law. Let us say we have this building here, and we are throwing this ball from the top of the building to the ground. Something like this. In this case, if you look at the ball closely as it is falling on the ground, you will notice something interesting. Look at the forces acting on this ball. The buoyant force, because of its motion through the air, acts on the ball, isn't it? The buoyant force is a force that acts on any body immersed in a fluid. We will learn more about buoyant force in the chapter Fluid Mechanics. So the buoyant force acts on the ball. The viscous force acts on the ball upwards, since the ball is moving downwards. The gravitational force, of course, acts on the ball. Now the interesting thing is that there are two upward forces also acting on the ball, just as gravity is acting downwards. Therefore, it is possible that at a certain point along its motion, Fb plus Fv can be equal to mg, isn't it? All the forces on the ball may become balanced, and that might mean that the ball may actually fall down with constant velocity instead of accelerating due to gravity. The value of Fb and Fv is generally very less. That is why we have neglected the effects of buoyant force and viscous force so far in our discussion related to falling balls. However, it is possible that Fb plus Fv can be equal to mg. If that happens, the ball will fall down with constant velocity. Let us consider the condition for which Fb plus Fv is equal to mg. The value of buoyant force is given by the expression density of the fluid into volume of the body into g. Of course, you will learn this formula in detail in fluid mechanics, but for now remember that the buoyant force on a body that is fully immersed in any fluid is density of the fluid into volume of the body into g. So rho L, where rho L is the density of air, into 4 by 3 pi r cube g is the value of buoyant force on this ball upwards. 6 pi eta rv is the value of viscous force, and density of the ball into volume of the ball into g, rho into 4 by 3 pi r cube into g. This is the weight of the ball. The sum of all these forces is 0. When you simplify this expression, everything cancels out, and what you get is the value of terminal velocity. You get the value of the velocity of the ball for which Fb plus Fv equal to mg. You see, if you look carefully, Fb is constant, isn't it? The buoyant force is constant. The gravitational force is also constant. Only the viscous force is varying, isn't it? It depends on velocity. So what happens is that as the sphere falls down and falls down, it keeps on accelerating. And because it accelerates, its velocity keeps on increasing. When it attains a certain velocity, the viscous force also keeps increasing, isn't it? It's proportional to v. So finally, at a certain velocity, viscous force increases to such an extent that it balances the rest of the force on the ball, and it puts the net force of the ball equal to 0. The velocity at which the viscous force and the buoyant force balance the gravitational force is called the terminal velocity of the ball. Understood? And this terminal velocity is given by this expression, 2 by 9 r square into rho minus rho L into g by eta. Here r is the radius of the ball, rho is the density of the ball, rho L is the density of air or the density of the fluid, and eta is the coefficient of viscosity of the fluid. This is the expression for terminal velocity, the velocity at which the viscous force increases to such an extent that it balances mg minus Fb. Let's solve a problem to understand this concept better. 2 raindrops are falling from a height of 5 kilometers towards the ground. The density of water is 1000 kg per meter cube. The raindrops are spherical and the radius of both the raindrops is 10 raised to minus 3 meters. The density of air is 1 kg per meter cube and the viscosity of air is 7 into 10 raised to minus 4 Pascal seconds. The acceleration due to gravity is 9.8 meter per second square. Find the height at which the raindrops attain terminal velocity. The terminal velocity of the raindrop that will be formed if both the raindrops merge to form another spherical raindrop. This question asks us a lot of things. First of all, we have to find the height at which the raindrops attain terminal velocity. So basically there are these two raindrops that are falling down onto the earth from a height of 5 kilometers. How do we find the terminal velocity of these raindrops? We can find the terminal velocity by using the formula we just found out. After all, a raindrop is also similar, to a ball falling on the ground. It's spherical. So Vt, the value of terminal velocity, can be given by this formula. Vt comes out to be 310.8 meters per second. This means that when the raindrops attain this velocity, in that case, the viscous force acting upwards on the raindrops will balance the force of gravity and the buoyant force acting on the raindrop. Now we have to find the height at which these raindrops attain terminal velocity. In this question, we can neglect the buoyant force, because the buoyant force is very less compared to the viscous force and the gravitational force. If we neglect the buoyant force, then the raindrop is actually attaining its velocity, its terminal velocity, only because of the acceleration due to gravity, isn't it? We will also assume that the raindrop is attaining its terminal velocity only because of the acceleration due to gravity. In that case, we can apply the formula v square equal to u square plus 2as to calculate, the distance traveled by the raindrop, after which it attains terminal velocity. Initially, the raindrop is at rest, and the acceleration of the raindrop is 9.8 meter per second square. Putting the final velocity of the raindrop as 310.8 meter per second, we get the value of distance as 4928.4 meters. So basically, this is the distance traveled by the raindrops, before the raindrops attain terminal velocity. Of course, this is just an approximate answer. In reality, buoyant forces will also be acting upwards, isn't it? In reality, even the viscous force will be acting upwards, isn't it? So this is just an approximation. If you want to calculate the exact answer, you have to equate the exact viscous force, that is 6 pi eta RV, plus the buoyant force to the gravitational force acting on the raindrops. If you simplify that expression, then you can get the exact value of the distance covered by the raindrop. Now it is given that the raindrops merge and they fall as one single large raindrop. We are asked, what is the terminal velocity of this large raindrop? Well, if you observed carefully, the terminal velocity of any body is proportional to the square of its radius. We just saw the expression. Since the radius of this large raindrop increases, the terminal velocity also increases. In fact, since it's proportional to r square, r1 square by r2 square is Vt1 by Vt2. Now the volume of the initial drop into 2 is the volume of the final drop, isn't it? So 4 by 3 pi r1 cube into 2 is 4 by 3 pi r2 cube, where 4 by 3 pi r1 cube is the volume of each of the individual raindrops falling down, and 4 by 3 pi r2 cube is the volume of the final raindrop formed after the initial raindrops merge. R2 comes out to be 1.26 times R1. Substituting that value in this expression, R1 square by R2 square is Vt1 by Vt2, we get the value of Vt2, the terminal velocity of the final raindrop formed, as this expression, 493.42 meter per second. All we basically did was we equated the volume of the two falling raindrops to the final large raindrop formed, the volume of that drop, to get the value of the final radius. And then we applied the formula r1 square by r2 square is vt1 by vt2 because the terminal velocity of a sphere is proportional to its radius. There you go. We've got our answer. To learn more about how to solve this problem, do log on to TopCoaching.com's physics section. Here's yet another problem. This was asked in IIT JEE 2004. A small sphere falls from rest in a viscous fluid. Due to friction, heat is produced. Find the relation between the rate of production of heat and the radius of the sphere at terminal velocity. Well, this question seems to be slightly complicated. After all, how is heat being produced?